Hello everyone. Today I have the privilege of presenting our work towards cost-effective and resource-aware aggregation at Edge for federated learning. This work has been done in collaboration with various researchers from Virginia Tech, University of Virginia, University of Minnesota, and this work has been partially sponsored by the National Science Foundation of United States. Recently, we have seen an exponential growth in the number of IoT and edge devices around us. According to a recent survey, the number of IoT and edge devices connections grew by 18% in 2022, up to 14.3 billion active IoT endpoints. And a forecast by International Data Corporation (IDC) estimates that there will be 41.6 billion IoT devices by 2025. As the number of IoT devices increase, the data generated by them also increases. Approximately all IoT devices have sensory hardware that observes or interacts with the environment. These sensors generate data when they interact or observe their environment. According to the estimate by IDC, by 2025, these IoT devices will be generating 79.4 zettabytes of data. This huge amount of disaggregated data is kept on different IoT endpoints. This fresh data is much more useful for analytics and learning applications than the stale data present in large data silos. According to a recent research survey conducted by a dimensional research for data integration specialist Fivetran, about 80% of companies are making decisions based on the stale data. For utilizing the large amount of fresh data generated by IoT devices, for applications such as machine learning, this data needs to be transferred to data silos, where high-performance computing can be used for training AI models. However, there are several challenges associated with transferring this much amount of data over unsecured network connections to an unsecured location. Firstly, the data generated by the IoT devices is highly sensitive. It can include personal information of individuals and entities. This information cannot be shared without their consent. In addition to this, there are several privacy laws, such as GDPR and HIPAA, that prohibit the transportation and storage of this information outside of where this information was generated. Secondly, transferring this data has a very large communication cost. Depending on the number and type of IoT devices, the data size can go up to several petabytes. To counter these issues, federated learning, or FL in short, has emerged as a powerful approach, enabling collaborative distributed model training without the need for sharing data. In FL, instead of transferring data from IoT devices to a central server, only the model weights are transferred. FL uses model parallelism to train the models, so it also does not require high-performance architecture. By taking advantage of model parallelism, it also improves the efficiency of overall learning process. To provide some background, in FL, a central aggregator server broadcasts the model to be trained to each participating client device. All the client devices then train those models in parallel. Once trained, each client device will send back the model to the central aggregator. The aggregator then fuses all those models to generate a single learned model using a fusion algorithm. Fed average is one such popular fusion algorithm that utilizes weighted averaging. Once those models are aggregated, the server sends the models back to the client devices for training. This process continues for a designated number of rounds or until the convergence is reached. The aggregator server that performs the aggregation and orchestrates the whole FL process is usually located at edge data centers with the client devices instead of placing it at a remote cloud server. This deliberate decision is made to reduce communication costs between clients and the aggregator server. However, keeping the aggregator at edge raises several challenges. The aggregator workload varies dynamically due to two major reasons. First, client model updates can be of different sizes. due to communication optimization such as quantization, pruning, etc., that are used for managing communication costs. Second, the number of participating clients also changed dynamically due to high number of failures in IoT devices due to reasons such as unavailability, low network, CPU, memory, or even software failures. Lastly, the aggregator server itself has low resources at the edge data centers. This requires efficient resource utilization of resources for the dynamic aggregation workloads. Furthermore, the aggregator needs to maintain the necessary quality of service demand of improved efficiency, all the while making sure that it can scale up if the workload increases and scale down to reduce costs. Efficient aggregation is important because during aggregation time, all the client devices are waiting for the aggregator's response. In this work, we propose several approaches for aggregation. Some of these have been inspired from prior works in the domain of parameter servers for cloud computing. Each technique has its own pros and cons, as also highlighted by the table. The single node technique is adopted by popular frameworks such as IBM Federated Learning, FedScale, and Flower, and even TensorFlow Federated. We enhance the single node architecture with parallel processing using Numba for improving time to aggregation. The hierarchical aggregator server is a distributed approach that was adopted from Vonowitz et al.'s paper towards federated learning at scale system design, published in MSys in 2020. It uses a master worker architecture for horizontal scaling, but does not consider cost or aggregation efficiency. Similarly, the serverless approach adopted from Jairam et al.'s work, Lambda-FL, serverless aggregation for federated learning, in FLAAI 2022, only considers cost but overlooks the overall aggregator efficiency and also the scalability of the aggregator. In this work, we aim to create an adaptive aggregator design that can utilize the best attributes of each of these techniques. In short, the adaptive aggregator should be adjustable according to the user needs to preserve cost and improve aggregation efficiency without compromising scalability. In addition to this, just like current parameter servers, the adaptive aggregator must also support multi-tenancy without compromising the quality of experience of any user. To realize these goals, there are several challenges that we need to resolve before that. The first challenge being how to enable compatibility between these methods so that they can be used under one system. Each method has its own architecture and data flow graph. The second challenge for realizing the adaptive aggregator is how to determine the correct aggregation method according to the user requirements under diverse workload and system conditions. To resolve the first challenge of compatibility, we combine the data plane for all of these methods so that all these methods use the same data source. In our particular design, the data store that we use for this purpose is a distributed, highly available database such as S3 or HDFS that can receive data from a large number of clients without denial of service. In the second challenge, each aggregator method has different cost to aggregation efficiency trade-off. Recall that the multi-core single node approach is most efficient for smaller workloads. The serverless is less costly but less scalable too. Similarly, Spark-based aggregator is more costly but scalable for large workloads. The aggregation efficiency also varies with workload for all three methods. Thus, the three most important factors to consider are cost, aggregation efficiency, and aggregation success. The aggregation success makes sure that we choose a method that is scalable enough to handle the incoming workload. To optimize this wide search space, we use reinforcement learning, or RL in short, that can adapt to varying conditions. In particular, we use a Q-learning based RL agent. The agent takes some state environmental parameters and outputs an action. After performing that action, the system produces a reward based on what was achieved by performing that action. The RL agent learns to optimize its future decisions based on that reward. Thus, the convergence of an RL agent highly depends on the predefined state and reward parameters. For the state of the RL agent, we use task-specific information that describes the characteristics of the incoming workload. The other state matrix is the system information, which includes resource availability information of the aggregator. In particular, it includes information such as available memory, available CPU, and the number of available executor containers in Spark or functions in serverless. Based on the learned perceived rewards of all the states, the RL agent will choose an action for this particular state. After the action is executed, meaning that the aggregation method that was chosen has been used for aggregation. If aggregation succeeded, the cost and aggregation efficiency will be recorded and used as rewards for fine-tuning the RL agent decisions. The following slides give a visual depiction of the RL agent training process and the overall system design. First, the RL agent receives state information including system parameters and workload information. In the second step, the RL agent chooses an action, which is the aggregation method to use for those particular state conditions. Lastly, the RL agent receives rewards for the action it chose and fine-tunes its decision process with these rewards using a process called Q-learning. For the implementation and evaluation, as described, we use three aggregation approaches in our adaptive FL aggregator. The multi-core approach of Number with IBM Federated Learning, two multi-node methods using PySpark with MapReduce for aggregation, and serverless running on AWS with FreeReduce algorithm for aggregation. We also use a client emulator that can emulate millions of devices in different regions of the world and can also emulate device dropouts, a common phenomenon in federated learning. Our dataset includes popular CNN models of sizes ranging from 4 MB to 1 GB, including models such as VGG16 and ResNet50. Our baselines include IBM Federated Learning Aggregator, which we also call vanilla, and the static aggregation methods such as the multi-core with Number, Spark-based MapReduce approach, and the serverless tree reduce for aggregation. Our evaluation objectives include the exploration of aggregation scalability and efficiency of vanilla, the exploration of aggregation scalability and efficiency of vanilla versus the static methods, and lastly, we want to find aggregation scalability, efficiency, and cost of adaptive versus the static methods. For simulating millions of clients for our evaluation, we use the client emulator. The client emulator can generate clients in different regions of the world, such as shown in the table. And it can also simulate models of different types and sizes. Similarly, it can also simulate the number of dropouts that the client wants to achieve. For example, we can see in the left side of the table, we have the client simulated with no dropouts at all, which means that all the clients are participating. In the right-hand side, we have 5% of dropouts, which means that randomly 5% of the clients will drop out due to random failures. Here we show the results of our first evaluation objective of aggregation scalability and efficiency using popular FL frameworks such as IBM Federated Learning. The total memory used here is 170 GB. As we can observe, the aggregator is unstable and crashes as the size of the model or the number of clients participating in the FL process increase. For our second objective, we show the aggregation scalability and efficiency of vanilla versus the static methods. In this particular result, we compare vanilla with the multi-core number aggregation method. We can observe considerable gains in the form of aggregation efficiency. In particular, we see a 40 to 57% reduction in aggregation time with number compared to IBM Federated Learning Framework. Similarly, this result shows the same evaluation comparison done with Spark MapReduce in comparison to IBM Federated Learning. Here we can see a 2 to 200 times reduction in aggregation time, even more than what we observed with number. For our last evaluation objective, we show all the static methods in comparison to our adaptive federated learning aggregator and we compare the aggregation efficiency and total aggregation cost. We can observe that the adaptive aggregator can take intelligent decisions to considerably reduce the aggregation time by up to 500 times and reduce costs by up to 3 times compared to static aggregation methods. We also evaluate the multi-tenancy support in our adaptive aggregator. The results show that it can easily handle multiple federated learning jobs at low cost and high efficiency. To summarize, the current federated learning aggregators are slow and expensive. The adaptive aggregator proposed on the other hand improves both the aggregation efficiency and cost. The adaptive aggregator can also be fine-tuned for managing the cost versus efficiency trade-off by adjusting the RL agent rewards weightage. Furthermore, the adaptive aggregator also supports multi-tenancy. For any questions or feedback, please use this contact information. If you are interested in this work, you can also check out other cool projects being done in our DSSL lab at Virginia Tech.